Hi, today in this video, first, I'm losing my voice a little bit, but we're going to look at 3.5, specifically the questions 25, 35, and 55. And what 25 says is factor completely, find all the zeros, state the multiplicity of each zero. For 25, this one catches a lot of students off guard because we've got like a 4 here and there's not really any evident, like any clear things that we can do. But if you remember factoring in either like 10, 10, 10, 15, whatever, the class preceding this, we learned about the difference of squares, where if it was something like x squared minus 1 or something like that, we would know, oh, it's going to be x plus 1 and x minus 1. Basically, we have a plus and a minus, and what goes there are going to be like the square root of both of these. And that is no different from what we're going to do in this case as well. We're just going to do the square root of both of these. So x to the fourth square root of that is x squared. So we will have x squared, and then we'll have the square root of this, which is plus 1 or minus 1. And we are not including the negative inside our square root. It's just how we do like the difference of squares. It's basically, yeah, if you're confused on that, just let me know and I'll send you another video on this because I have one. But yeah, so this was getting the factors, but to find the zeros, we can set these equal to 0. Let's start with this one since it's going to be nicer. We'll have x squared is equal to positive 1. Take the square root of both. We'll get x is equal to plus or minus 1. And then for this one, it's a little bit meaner because we have to deal with some irrational, imaginary numbers. Not irrational, it's just imaginary. And so we'll square root both sides. And we'll get x is equal to plus or minus I, because I is equal to the square root of negative 1. So those are your zeros, and the multiplicity of each zero is just 1. So I, 1, negative I, 1, 1, 1, negative 1, 1. And that would be your answer for 25. 35 is a little bit different. It's got x to the fifth plus 6x cubed plus 9x. Now, the first thing that we can do is just take a GCF. That's going to help us quite a bit. So x to the fourth plus 6x squared plus 9. Now, this is similar to this problem. You're going to see a lot of these examples where it's sort of like factoring. I don't remember the exact term. I think it's factoring in form or something like that. Where because if we divide this term by 2, we'll get this exponent. So like 4 divided by 2. This would be factorable as a polynomial, or 2 divided by 2, which is equal to 1, right? If you had something like x to the sixth and 6x to the cubed plus 9, that would also be factorable. We want 2 related terms like that. So what we're going to do is we're going to treat this like a normal polynomial. Firstly, right off the bat, we know that we have a 0, and the multiplicity is 1 of that. At least so far. There might be a 0 here, but I doubt it, because of this x. Next, though, what we can do is 1 times 9. I'm just going to use the AC method or hippo butts. I call it hippo butts. If you're not familiar with the term, that probably catches you off guard. It's just a method that I learned in a different class under a different instructor. She had like a banjo and everything. She'd bring it, and there's a whole song. But anyway, 9 split up to add up to positive 6 is probably 3 and 3. So we will have x times x plus x squared plus 3, because we've got a squared term in the middle here, and x squared plus 3. So it's going to be x times x squared plus 3 squared. But it wants us to find all the zeros and their multiplicities. Now, since I have a squared here, I know that the multiplicity of each of my zeros in here are going to be 2. So let's set this equal to 0. We have x squared is equal to negative 3. X is equal to plus or minus I root 3. I did that very quickly, but basically I took the square root of both sides, took out an I because we can't have a negative inside of there, and then plus or minus it. And both of these, again, have a multiplicity of 2. So we will have 0 mult 1. We will have positive we don't need to write the plus sign, I root 3 root 2, and we will have negative I root 3 multiplicity 2. Now, all of your multiplicities should add up to your leading term, which was a 5 in this case. So, 1, 2, 3, 4, 5. Sorry, not your leading term. Your leading terms, the degree of your polynomial, which tends to be the leading term's exponent. Hopefully that makes sense. Moving on to 55, it's asking basically the same question. It just says find all the zeros of the polynomial. It's not saying anything about multiplicities or anything. So this one, we're going to have to employ some of the techniques that we learned in 3.4 with just kind of narrowing this down a bit. So I'm going to do the rational zeros theorem first. So what are all the factors of 18? So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, and plus or minus 18. So these are all of our possible zeros. Next, I'm going to do Descartes' rule of sign to figure out which ones might be applicable. So I have one positive real zero. And then I'm going to flip the signs of the ones that are negative, not negative, odd exponents, which is basically the same. I'm doing f of negative x, but I'm doing it in a simpler way. Minus x cubed plus 7x squared minus 9x minus 18. Looks like there's 1, 2, 3. So 3 or 1 negative real zeros. I have a feeling, since we're in chapter 3.6, that we're probably going to have one positive real zero and one negative real zero, and the other two are probably going to be imaginary. But with this in mind, let's start doing some synthetic division. So we're going to put, I'm going to try positive 1 first. So I have 1, 1, 7, 9, negative 18. Don't forget placeholder zeros. In this case, it's not really applicable. Drop the 1, 1, 2, 2, 9, 9, 18, 18. Awesome. 1 was a 0. Now we can work with this problem, which is 1 x cubed plus 2x squared plus 9x plus 18. Now, I think it's useful to be looking for specific relationships. I know that 9 and 18 are related, so it's a good try. It's like a good step here to say, okay, I'm wondering if this can be factored by grouping. A lot of times it won't be able to, and you'll need to continue going through with synthetic division, but in this case it looks like it might. Let's take out the GCF of this side, which will be x squared, which will leave us with x plus 2, and then let's take out the GCF of this side, which will be 9, which will leave us with x plus 2. That looked awesome. That worked out really nicely for us. So we know, and then let's take this one and turn it into a 0, so we'll have x minus 1, because it's basically x minus our 0, and then let's put the x plus 2 here, and the x squared plus 9. So I know that I have an x equals positive 1, x equals negative 2, and I know this is going to be imaginary because it's a plus 9. So let's set this equal to 0. X squared equals negative 9, because I minus 9 from both sides, square root both sides, and you will get x equals plus or minus 3i. Because the square root of 9 is 3, and we're taking out a 9 because there's a negative number on the inside there. So then we'll have x is equal to 3i, and x is equal to negative 3i. Now, it doesn't ask us to put it into factored form. That's all we need to do. That is all the zeros of that equation. If that did not clear things up, please let me know, and I will answer as soon as I can. Have a good one.